You hit enter, and a page appears. But between that request and the pixels on your screen, your browser does an enormous amount of work, and almost all of it happens on a single thread. Let's slow it all the way down. Your browser is, at its heart, one worker, doing one thing at a time. Understand how that one thread schedules its work, and everything, from a frozen tab to a slow page, suddenly makes sense. Here's the foundation. Your browser does almost all of its work on one main thread. It runs your code, it figures out where everything goes, and it paints the result. One worker, handling one task at a time. So the order it does things in, and how long each thing takes, is everything. Zoom into that one thread, and you find the call stack. Call a function, and the browser pushes a frame onto the stack. That function calls another frame, stacked on top. When a function finishes, its frame pops off. Last in, first out. This is synchronous code, one frame at a time, each running to completion before the next. And while there are frames on the stack, the thread can't do anything else. Now here's the problem. If one of those functions is slow, a giant loop, some heavy work, its frame just sits on the stack, and because the thread is busy with it, nothing else can happen. The page can't repaint, it can't respond to a click. This is what a frozen tab actually is. The main thread, stuck on one synchronous task, with everything else waiting behind it. Asynchronous is the way out. Instead of doing the slow work on the main thread, the browser hands it off to its web APIs, which live outside your JavaScript. A network request, a timer, reading a file, all handed off. The main thread is free again. Your code keeps running, the page keeps painting, and the slow work happens somewhere else, in parallel. So the slow work finishes somewhere else. Now what? Its callback can't just interrupt whatever's running. Instead, it goes into a queue. And this is the event loop. A simple rule, repeated forever. Is the call stack empty? If yes, take the next callback from the queue and run it. If no, wait. That loop is how a single thread juggles everything, without ever doing two things at once. Here's the part that trips people up. There isn't one queue, there are two. Promises go in the microtask queue. Timers, like set timeout, go in the macrotask queue. And the rule is, after each task, the browser drains the entire microtask queue before touching the next macrotask. So a resolved promise always runs before a set timeout of 0, every single time. Now you know why. But running your code is only half the story. To actually show a page, the browser runs a pipeline. It parses your HTML into the DOM, a tree of elements. It parses CSS into the CSS-OM, a tree of styles. It combines them, then does layout, calculating the exact position and size of every box. Then it paints, filling in pixels, layer by layer. And finally, it composites those layers into the frame you see. Change one thing on screen, and parts of this pipeline run again. And that's the whole trip. The request comes in, the browser builds the page, and runs your code on that one thread. The slow work goes off to the web APIs, and the moment its result comes back through the queue, the event loop runs it, and the browser paints pixels on your screen. That's everything that happened between you hitting enter and the page appearing. So here's the whole model in one breath. One main thread, synchronous code blocks it, asynchronous work frees it. The event loop runs finished callbacks the moment the thread is clear, microtasks before macrotasks. And the render pipeline turns your code into pixels. That's what your browser is doing while it waits. But notice what we assumed this whole time, that the server was already there to answer. Before any of this, your browser had to find it, translate the name you typed into an address it can actually reach. That's DNS, and it's where we go next.